Hello everyone, this is Satya, and this is our final project based on neural networks for the sequence data. And this project is about the time series data. This project is about the time series data set, and this and here, as you can see here, we which is a light delay causes data set. I'm going to explain the precise information about the time series data set which we have considered here. So this data set provides valuable insights into the on-time performance of the airlines in the United States from October 1987 to the April 2008, containing roughly 130 million records. Oh, as it also includes retail information for every commercial flight of offering a comprehensive picture of delays, cancellations, and diversions. So entering into the key points, I would say the data span is from October 1987 to the April 2008. And the data points for this data set would be 130 million records. And the data size is about like 1.6 GB compressed and 12 GB uncompressed data source. And this data source is data and we have extracted this data source from the Kaggle. As you can see the Kaggle link provided here. And the data structure includes the departure and arrival, flight numbers, carrier codes, delays, cancellations, and more. So the US Department of the Transportation, which is the Tier Bureau of Transportation Statistics, BDS, tracks the on-time performance of the domestic flights operated by the large air carriers, and the potential uses of this dataset can be analyzed causes of the delays and cancellations, and also identify trends in on-time performance, which uses in developing the predictive models for flight delays, evaluate airline performance, inform policy decisions related to the aviation safety and efficiency, and the benefits would be considered as a large and comprehensive data set covering a long period detailed information on the individual flights publicly available, and it is free to access the support, research, and analysis of the airline on-time performance. And the future of the application would be of machine learning models, which is used to predict the delays and cancellation, and also develop the real-time passenger notification systems, optimize the airline operations, and the scheduling call to action for this data set can be this. This dataset offers a valuable resource for researchers, analysts, and anyone interested in the performance of the airline industry. By exploring this data, we can gain valuable insights into the improving the reducing delays and enhancing the passenger experience. 3015. So, enhancing the overall passenger experience. Hence, it shows all the results that are causing the factors, the delay. As you can see, the information which we have, all the data sets about the data points, how long the period is, and how the data content is in the data set. So the data number is basically numeric, presenting the new number of days and the number of origin lines. The data is also numeric, and here comes the part two. And the part two is a simple RN with a sine wave. The train and evaluate a simple recurrent neural network that has two layers, one in a simple AR and a fully layer in the cases. So today we embark on a journey into the intricate world of recurrent neural networks, especially focusing on a simple RNN architecture. Using the Keras and the sine wave dataset, this neural network, often referred to as a vanilla RNN or Elman RNN, possesses a single hidden vector or making it a vector edge. So our exploration begins with the construction of a time series generator where we generate a sine wave data to stimulate the unpredictable of flight delays. Leveraging the NumPy library, we create the 768 data points representing the sine waves values over a range of 0 to 50. And this is a code for the above explanation to generate the data code, like how to generate the sine waves. We will utilize how we utilize the space function of NumPy first, and the 760 data points representing the sine waves values over a range of 0 to 50, as you can see here in the split the data. As you can see here, the split data, train data. So to ensure a robust evaluation, we split the data into the training and testing sets with 20% reserved for testing the minimax scalar 8. In the normalize is in the data crucial for the subsequent creation of a time. So for the time series generator, the generator utilizes 50 past data points for the forecast, future values, setting the stage for our real neural networks. And here is the below code provided. Here is the below code provided in the screenshot. So we will consider the time race in it, time race input sequence, the time series generator, and the length of the tree size for the sequence. We must fit the simple sample to the model. When we train or test it, or to ensure, so the next thing is going to be build and train. So building the recurrent model involves creating the simple RNN layer with 100 neurons, capturing the essence of a vanilla RNN. So we employ the mean square error, which is MSC, and a cost function given the continuous nature of our data points with the over 10,000 parameters created across the layers. Our neural network is ready for training next. So the next slide is going to be the train and fit. And this is the training process involving the using a fed generator approach where the time series generator injects input data in the batches. We train our model over 5 epochs, each epoch representing an iteration over 770 data points. This loss function provides insights into the model performance, indicating a continuous improvement in accuracy. And finally, the next slide is going to be the evaluate model on the test data. As we transition to evaluating the model on test data, we extract the most recent 50 data points to anticipate future values. The model predictions are then compared to the actual sine wave values, visualized through a graph. And here the blue line represents the actual values, where the yellow line showcases the predicted values. As you can see in the screenshot, the blue line represents the actual value and the yellow line showcases the predicted one. So, so as a summary, I can say that our exploration of a simple new recurrent neural network using Keras and sine wave data set highlights the power of the RNNs in capturing sequential patterns from data generation and pre-processing to model building. And evaluating this journey offers a comprehensive understanding of the intricate dance between the neural networks and intimate time series. So now let's get into the part three, which is the LSTM neural network. So the question 3.1 is about the explain the vanishing gradient problem. I'm explaining the exploring gradient problem. So the record neural network evaluation, reevaluation, that is the machine learning by enabling the analysis and learning of sequential data, offering applications in diverse fields like stock market, prediction machines, translation, and text generation. What challenges do we face for training RNNs? So challenges of training RNNs. So while RNNs are powerful, they face severe limitations. One primary challenge is training the fundamental structures of the RNNs makes them susceptible to the vanishing and exploring gradient problems. During the backpropagation to through time, vanishing gradient problems. So the vanishing gradient problems is going to be the vanishing uh, occurs when the gradients becomes exceedingly small during the training, rendering, weight updates. So this phenomena indicates the learning process, especially over the long sequence exploring gradient problems. So here, when gradient becomes extremely large, destabilizing the network and hindering effective learning, both problems are consequences of the chain rule applied. So uh, what is actually LSTM? So it is a long short memory neural networks. To address these challenges, LSTM networks were introduced by SE, um, and the LSMs have proven effective in sustaining error throughout the backpropagation over time and layers, facilitating consistent learning over extended sequence. What would be the key concepts of LSDM? What would be the key concepts of the LSTM? So after looking into it, we can say that um, the core concept of the LSMs are cell state, which we call as a C state, and the gate lumps feature three crucial gates: forget gate, input gate, and the output gate, each using the hyperbolic tangent and the sigmoid activation functions. So the LSTM solution for the to the gradient problems would be let me have a look into it. Um, TM limitations. Let's just cover this. So here the robust solution to the both vanishing and the exploring gradient problems through the unique architecture, the Fargate So the forget, which controls what information in the cell state to forget, plays a pivotal role by allowing the networks to selectively retain to the and back propagation through times in the LSTMs, and this would be the during the back propagations. So um, LSM cell, the LSM cell here, additive structure and the presence of the forget gates activations contribute to preventing gradients from vanishing the addictive property of a cell state gradients, enabling better balancing of values and also reducing the likelihood of conversions to zero limitations. And the conclusion of the RNS would be the limitations. As you can see here, the limitations and conclusions. While RNS paved the way for the sequential data analysis, the limitations necessitated the development of more advanced architectures like LSMs, RNNs, fed challenges such as load training procedures, difficulty in processing the longer sequence, and the inability to be stacked for the parallelization. As we look ahead, mm, as you as we continue to the vanishing exploding, so we have the question in the 3.3. As we look ahead, we continue to explore and enhance the neural network architectures, understanding these challenges and solutions. It propels us towards a more sophisticated models capable of handling the integers of the sequential data. As you can see, when diving into the theory behind the recurrent neural networks and the long short memory, which is LSTM networks, there are two main questions arise. Why do the RNNs suffer from vanishing and exploding the gradients? And how do LSTMs keeps the gradient from vanishing or explode so after reading the recommended papers and known blogs dealing with these questions, I wrote an explanation that worked for me and made me feel I better understand the problem and the solution. RNNs and vanishing gradients enable the modeling time dependent and the sequential data tasks such as stock market prediction, machine learning, text generation, and many more. However, RNNs suffer from the problem of vanishing gradients, which hampers learning of a long data sequence. The gradients carry information used in the RNN parameter update when the gradient becomes smaller. And the smaller the parameter updates become significant, which means no real learning is done. As you can see, the network has a two weight matrices. Uh, Two-weight matrices where W is connecting the two paths for the input and the hidden layer back propagation through the time. And the B between the RNAs would be followed by the below formula. And the last expression tends to expression tends to vanish when K is large. This is due to derivative of tan H activation, which is smaller than 1. So these are all the formulas and the calculation for the LLM network that has an input vector at the time step. And this is the LSM input gate update of the cell state, the inputs the input gates outputs has the form of the output gate activations are given by this below formula, as you can see here in the following slides. And also the complexities of the IRN. Oh, so the complexities of the RNNs, the vanishing and exploding gradient problems, and the IGN solutions offered by LSTM network is a evolving field of machine learning. And these insights pave the way for even more innovative developments. And the main disadvantage of the RNNs are speaking of the disadvantages, the main disadvantages of the RNNs are training RNNs, the vanishing or exploding gradient problems, as you have seen in the above slides. Uh, as you have seen in the above slides, let me explain about it. As you have seen in the above slides, RNNs cannot be stacked up because they have the gradient problems. They cannot be stacked up, and slow and complex training procedures. One of the biggest disadvantages is to difficult to process the longer sequences. So these are the disadvantages of the RNNs. Um, and coming to the fourth part, as you can see, the fourth part, which is the LSTM with the time series data. So I'll walk you through a comprehensive project utilizing long short memory, uh, which is LSTM network for the time series predictions, um, which is specifically applied to the stock price data. We begin by importing essential libraries, including the cases for the billing neural network. So the dataset boasts 2582 instances, each with 7 attributes, showcasing stock, showcasing the stock related metrics. After exploring and visualizing the data, uh, we dive into the time series, creating sequences of 60 historical data points. And the next, we will split it into the we'll split it into the yeah. As you can see here, the next we'll split our dataset into a training and testing dataset with 10% reserved for testing, normalizing, and the data using Minimax scalar enhances our modes performance, employing the cases time series. As you can see here, 50 historical data points were used to predict this data. And yeah, and testing normalizing the data set using the minimax scalar enhances our model's performance, employing cases time series generator. So we generate batches for efficient training. Our neural network architecture involves two LSTM layers with 25 neurons, each followed by dropout layer to prevent the overfitting. So, training over the 100 epochs on 37 patches, our model exhibits decreasing loss, indicating improved accuracy during the training. We visualize predictions and assess performance for testing, we evaluate the model on a separate set, demonstrating its ability to predict future stock. Our approach combines LSDM and simple RNN layers, offering a robust framework for the time series. Forecasting, and here is all the explanation about it in summary. So our project employs a multi-layer LSTM network with dropout layers utilizing the 10% for testing 100 epochs and 32 sample batch size. So the model showcases the strong predictive capabilities, demonstrating the power of LSDM in capturing intricate temporal patterns with stock data to generate the input sequence and the batches to fit the for the model in 0.01%. So in the model 0.01% is used to drop the number of edges is 2718 divided by 32, which is 84 each percentage. Um, and it has a 34-35 samples. The sequence is used to so the sequence is used to predict the next value at index 60. We have used the 100 epochs for time series and the 40 epochs for the forecasting. And here comes the part 5, which is redesign the neural networks using the crucial thinking and the experience of the working with the time series. The student should propose some changes to the above network or the network training process with which the network performance may be improved. So let's explore and enhance the enhanced approach to time based prediction using the neural networks uh, specifically tailored for stock price. We kick off by importing the um, essential libraries, leveraging the Matplot libraries for visualization and adopting special time series recurrent neural networks RNN with a dropout for increased accuracy. So our dataset comprises of 2582 instances, each with the 7 attributes, including the integer base volume after carefully digging and selecting a time series sequence and splitting the data set. So splitting the data set into the training and testing the data set training and training and testing the data set with the 7 attributes including the integer base. So we move to normalize the data set with 0 to 1 range using the minimax scalar. So we offer a time series generator with a batch size of 40 samples, optimizing efficiency for our model. Here we choose to focus on the closing price attribute of our neural network, involves a LSTM layer procedures. So visualizing the LSTM layer. Uh, so the simple RNN layers, ERS with dropout layers to provide a models training process. So here, so as I said, to prevent the overfitting the model, the training processes 70 epochs with 40 batches per step, visualizing the model's predictions. During the training provides insights into its performance, and we evaluate its accuracy against a separate test. Uh, so in conclusion, as you can see here, so in conclusion, um, So yeah, sorry for that. As we coming into the conclusion, the redesigned neural network demonstrates a non-approach to the time prediction, redefining the training process and architecture for improved accuracy. We aim to redefine the dynamics of stock price forecasting by harnessing the power of LSVM networks with dropout layers, strategic data splitting, and thoughtful choice of the hyperparameters. So that's it with the part five. Next, moving on to the part six, which is the compare the network performance. So basically, we need to write a report on the result of comparing the performance of two networks and provide a reasonable explanation. So the the precise explanation of the LSM neural networks. So it is evaluated in the part three and the part four of our study. In our investigation, we meticulously examine the various factors, including dataset size and the quantitative evaluation to access the performance differences between the two networks in the part three. Our LSDM model underwent testing with a 10% dataset for the validation and 25 neurons in each layer, a 10% dropout rate. So, and a batch size of 32 and a 40 above. However, in the part 4, we implemented several modifications to enhance the performance. Notably, the test data set percentage was increased to 20%, and the number of neurons per LSTM was double to 50. So the dropout rate was heightened to the 20%, and the batch size for the training was increased to 40, and the number of the training epochs was like extended to the 100. So in the conclusion, while adjustments we made to the critical parameters such as the test data sets and the number of neurons, dropout rate, batch size, and the training AO. So this overall impact it impacts on the performance was limited. This indicates that our LSDM model, even with the alternation, maintain a relatively stable performance. That's good, right? So this for the further refinement may be necessary to discern more sustainable, substantial improvements in the network. As we move on to the, so that's it with the part six. As we move on to the part seven here, um, uh, it is a write an introduction section to the introduce the project. Um, so as we discussed earlier, our exploration of RNNS, we discovered the unique ability to incorporate the context from the previous steps, which is addressing the challenges in scenarios where sequential data dependencies matters, such as predicting the next word in a sequence. So moving on to the project key sections, uh, as you can see here, moving on to the project key sections. In the part two, we ventured into the world of the understanding data, understanding the data correlations and the patterns for the time series. Forecasting the part two shed light on the importance of the LSTMs in handling long-term dependencies, providing a non-solution to the limitations of standard RNNs. So our journey continues to the into the part four and part five, where we turn our model with the parameter parameter adjustments aiming to the optimizing performance throughout the experience. We have learned that RNNs are adapt at modeling times for sequence based data with application ranging from the natural language processing to the stock price prediction. So the change, it lies in the, so however, the change lies in the short-term memory. Um, so this is where the LSMs come into the play, showcasing their prowess in maintaining the both short and long-term memories, making them well suited for the intricate tasks requiring the deeper understanding of context. Um, so in the conclusion, I would like to say that the advantages and disadvantages of RNN would be introducing the fancy RNNs, LSTMs. We have de-evolved into the complexities of these networks, understanding that more control over the inputs and outputs comes with the increased complexity and operational cost. Our project not only provided insights into the theoretical aspects of these models, but it also involves practical hands-on experience, uh, loading the datasets, splitting them for training and testing the experimenting with LSTM models quicking. So for the parameters for optimal results in the essence, our journey through the RNNs and the LSMs has been an exploration of both theory and the practical implementation, offering a deeper understanding, which helps in strengthenings and limitations. Thank you.